In the last video, we learned about the Moivre's theorem and how useful it is to get the power of complex numbers. Now today we're going to use it again, but this time we're going to use it with non-natural numbers. That means the n doesn't have to be 2, 3, 4, 5, 6. We're going to use fractions. And that's going to be really useful for us to solve questions like this. So where w to the power of 3 is equal to this guy. Now we've been doing questions like this all along. That means w is equal minus square root of 3 plus I to the power of a third. When I say we've been doing this all along, I mean before complex numbers, just in the real numbers. We might have x to the power of 3 is equal 27. That just means x is equal 27 to the power of 3, to the power of 1 over 3. And that's simply equal to 3. Now, it gets complicated even with real numbers, because sometimes we might have x squared is equal, say, 4. That x is not only equal to 4 to the power of a half. X is not only equal to 2, it's also equal minus 2. It's equal to plus or minus 2. In real numbers, when we were to get a question like this, when we were to get something to the power, x to the power of something equaling something, we would always get two answers if it was a even number and one answer if it was an odd number. So it's a bit weird. It's going to get even weirder in complex numbers. When we take a complex number to the power of a fraction, we're going to get multiple answers. I'll try and explain why. And we'll see that as we go. I'll use this as an example so we can step through everything, and hopefully you'll see where it all comes from when I get to the end. But of course, as always, if you have any questions, put them in the comments below and I'll do my best to answer them. Right, the first thing we need to use the Moivre's theorem, because we're going to use the Moivre's theorem. It's very easy to get the power of things with the Moivre's theorem. If we do one thing, we change it from a rectangular form, the form lots of students seem to like, this is the one we learned to begin with, to this form here. This is much better if you ask me. But anyway, I understand lots of students still don't like it. But we already learned how to change from this form to this form. Let's do it again, as we have to sort of here. I like to draw a picture first. You don't have to. You can always remember that it's this number squared plus this number squared, the square root. That's Pythagoras' theorem, but I'll do it the long way. Let's see, we will need square root of 3. Let's put in minus 1 and minus 2 here, and we put in 1, 2. We're going to need 1 up here, so let's make this nice and big actually. Yeah, let's make this even bigger. Let's put it over here, because I just remembered what the answer is going to look like. Let's change this to be 0.51, 1.5, 2, minus 0.5, minus 1, minus 1.5, minus 2, and we'll just go up in halves. 0.5 and 1, minus 0.5, minus 1. That should be enough for us here. Now let's draw this guy. Minus square root of 3. If you look up square root of 3, you'll find something like 1.7, so minus 1.7, somewhere around here, let's say. And then plus I, that's plus I up here. So we get a point over here. That's what this point looks like in rectangular form. Well, it looks the same in every form. So remember how we do polar form. All we need is or, that's the length, the modulus, from here to the center. I won't ruin this picture here, but over here I'll draw this again. This length here. But remember, we can draw a little triangle. The height is 1. The length is square root of 3. So all I need is this number here. Well, that's square root of 3 squared is 3. 1 squared is 1. Square root of 4, that is. That's equal to. So that's we know the new length. I'll write that. I need to use my space correctly. So I'll write it here. I'll have to rub this out, I think. Okay, we also need to find this angle here. So we need to remember our trigonometry. Although we could use the 2 now, but usually we just use And let's call this angle phi. We use this number and this number. So again, you don't have to draw the triangle. Once you get very used to this, it's tan phi is equal 1 over square root of 3. So that means phi is equal the inverse tan of 1 over square root of 3. So lots of students, when you get used to it, you can jump right to here. You know it's always going to be the inverse tan, this number over this number. The y part, the imaginary part, divided by the real part. In fact, we can leave the minus number. It's going to get us the answer a little quicker. I like to draw it though. This tells me the answer is 30 degrees. This angle, that's not the one we want though. I want this angle here. I always want to start here. What is that angle all the way around? Well, if this one's 30, this one must be 150. So that's theta. Theta equals 150. Okay, so now I have enough to, instead of writing it this way, I can write it in the polar form. The form we need for the Moivre's theorem. Let me rub this out. We don't really need that, and it's going to get a little in my way. So instead of writing it this way, minus square root of 3i, I can write it 2 cosine 150 plus I sine 150. Very similar to this, there's really two pieces of information, an x and a y. In this one, there's two pieces of information, an or and a theta. They tell us how to get to this point just the same. Theta is the angle. I just realized how dark it is, so hopefully all the light has instantly changed for you. I've just turned the lights on. So as I was saying, theta is the angle that points this way, and or is the length. So if we go 150 is about here, and then we go out 2, gets us to here. Not 2 this way, not 2 this way, 2 out along here. Gets us to the same point. The exact same point. Now here's the interesting thing though. There's only one way to write it in rectangular form. There's only one way to get there in this form. There's not only one way in this, and this is where we're going to get different answers. We're going to get 3 different answers to the question. That's because the question, how to write this number, has infinite different ways. We can write this number infinite different ways. There's only one way to draw it. There's only one point on the screen to draw it, but there's lots of ways to write it. We can change the angle, infinite different angles. We've used 150 and gone 2. We could also use 150, well, let's say 360 and another 150. So that's 360 plus 150 gets us to 510. I could have used the angle 510 instead of 150. I don't have to use 150. I could have used 510. It would get the exact same point. It would equal this as well. It would equal this guy just as well. I just noticed I don't have square root of, power of 1 over 3. Or cube root, we sometimes call it. So instead of 150, I could have used 510. But it would look identical. But the answer is going to look different, and that's what's important. So as well as 510, I could have also gone around twice and then gone there. That would have given me 870. 870. I could have gone around 3 times plus another bit. 1230. I'm just going up 360 every time. This goes on forever. I could do many more of these. In fact, it can go the other way. How about instead of 150, what if I went minus? Minus 90, minus 180, minus 210 would get me to there. Yes, 210, minus 210. All of these ways to write this number are perfectly okay. And that's why we're going to get 3 different answers. Because although there's 5 different ones there, we're going to be able to get lots of different answers. In fact, there's infinite. This can go on forever. It can go on forever down as well. This is a good time to introduce the general form now. I haven't talked about it. It's not needed for this question really. A bit of an understanding of it is. So another way to write all of these numbers at the same time is, let's put it equals here. This will work. 2 I'll run out a bit of room, so it might get small on the camera. I apologize for that. 2 cosine 150 plus 360 n. So let's put in more brackets here, so instead of 150, I'm writing, so I'll run out a bit of room. So let me just talk about this because it's the same number. 150 plus 360 n. N is every number, it's 0. If I put a 0 in there, I'll just get 150. If I put 1 in, I'll get 150 plus 360, 510. If I put 2 in, I'll get 870. If I put 3, 1230. Hell, if I put minus 1 in even, minus 1 will give me 210. So any number that goes in there will give me any of these. So often they actually ask us to write the general form. And that's what it looks like. So this is, well, this is plus I sine the same thing here. I'm really not going to fit it in, I don't think. At least not enough for you guys to see on camera. And this is still to the power of 1 over 3. That's the way to write the general form. Though you don't necessarily have to. You have to understand a bit of where it comes from. But we wouldn't always write it out. We wouldn't always write it out like that. Okay, that's all the hard work. I promise that's all the hard work of this question done. And it wasn't really that hard, I hope, because we did it a couple of videos ago. Just the idea that there's multiple of them. And you'll see why in a minute. Because let's get the answer. This is to the power of 3. Let's do to the power of 3 then. It's easy with the Moivre's theorem. It's easy to get the powers. It just becomes, I have it missing here, or to the power of n should be there. So it's easy. It's just 2 to the power of 1/3. So let's write it, yeah, I'll have enough room here. Let me change the markers. So it's 2 to the power of 1 over 3. I'm just reading off the Moivre's theorem here, or to the power of n, or an n. And we're still multiplying by cosine. Instead of 150, we're just going to get n multiplied by 150. That's 1/3 multiplied by 150. A third of 150, that's just 50. Plus I sine 50. That's it. That's 150 done. That's how easy the Moivre's theorem is. We can get the cube root, the power of 1 over 3, really quickly. This is a answer. I was going to draw it in, but no, let me do all the answers first. Because I didn't have to use 150. I could have used 510. Now you'd expect I'd get all the same answers, but I'm not going to. If I did 510, everything else would be the same. 510 divided by 3 is, I hope I have it here, 170. 170 again here. If I did 870, I would get 290. Just put it on a calculator. Just divide it by 3. 12,030. 1,230. I can do that in my head. That's 400 and another 10. 410. And let's not forget the minuses. This goes on forever, remember? As long as this says going on, this one says going on. The minus would be divide that by 3. Again, that's an easy one to do in your head. Minus 70. Minus 70. So there's many different answers. But here's the interesting thing. With the starting guide, all of these answers looked like this. They all look the same. They all look like this point here. But the answers don't. Let me draw in what they look like. Let me change color pens here. Let's do the first one. Well, first of all, 2 to the power of 3 is about 1.26. Let's say 1.3. Somewhere in, let's say here. And, oh, well, no, I'm not going to draw it there. Sorry, that's just the length of the radius. Let's do the angle first. 50 degrees. There's 45. So I'd say about here, about 50 degrees here. And we need to go out this far. We need to go out 1.3 far. So let's see, if we rotate that around, I'd say about there is my guess. So that's one of our answers. That's a perfectly valid answer. If we get this number to the power of 3, we'll actually get here. So that's, I love complex numbers like that. We're turning multiply into this image thing. Multiplying this point by itself 3 times, we'll get it all the way over here. But there's more other answers that are going to look different. Maybe you see already how much they're going to look different. 170, let's try and draw that one. Here's 180, so it's a little above here. And if we rotate this up, I'd say about here. That's another perfectly good answer. Here's one answer. Let's put in their lines, maybe, so we can see them a little bit better. Use a black marker. Here's the original one. Like that. So there's two answers. Let's stay going here. 290. Here is here's 360. So we need to do 70 degrees away from that. That'd be somewhere down, I don't know, about something like that maybe. And what we're going 1.3, somewhere like over here, I think. My drawing's not the best. These all should be the same length. All the red lines should be the same length. But that's the fault of my graph more than anything. Okay, let's stay on. What about 410? 410 is 360 plus another 50. Well, that's here. We already have 50. And the same length. The length hasn't changed. So we're going to get the same point. If I did another one, the next one up, I'd get this point. If I did the next one up, I'd get this one. The next one, this one, this one. We'll stay getting the same tree over and over. So there's only 3 answers. There's infinite answers, but 3 of them are all identical. All of them are identical to one of these 3 answers. If we went down minus 70, here's minus 70 down here, we'll get the same answer again. So really, I only needed to look at 3 of these numbers. And we usually just use the first 3. And they would have given me these 3 answers here. These 3 answers are all I needed. Now, I could have looked at any group of 3 as it happens. But we just tend to look at the 3. At least I tend to always go up like this. If you look at a more general form, it still makes sense if we look at this general form here. Let's use the Moivre's theorem on this guy. It will still equal 2 to the power of 1 over 3. We'll still get cosine. We'll get 150 plus 360n divided by 3. Well, that'll just become 50 plus 120n. Plus I sine 50 plus 120n. I hope you can see all that, because that's all of these answers here. It's 50 plus another 120, another 120, another 120, stay going forever, or minus 120, stay going forever. And that's because the question will always look the same if we add 360 to it. So the answer, because we're using 1/3 here, we're using 1/3 of 360, 120. And then we have to think of the world where it repeats itself is inside a circle. So all of these are unique. So basically, how many times does that 120 fit inside a circle? So that's why we get 3 different answers. If we got to the power of, if the question had been w to the power of 20, we would have got 1 over 20. We would have had 1 over 20 multiplied by this 360, which would have given us 20 different answers would have fit in this circle. And they're all quite unique. This answer could never be the same as this one. It would never be in the same point until we went around the circle an entire time. So we'll always have the number of answers that the power is here. Okay, so that's the 3 answers. I guess we could put this into a calculator to get it back into this form. We just need to multiply this out. 2 to the power of 1 over 3 multiplied by cosine 50. Put all that in a calculator, you'll get 0.81. That's rounded to 2 decimal places. Again, this multiplied by sine 50, you'll get plus 0.97i. There's an I here. So that's roughly this point here. My drawing is not too bad. Nearly 1 and nearly 1. So that's where that point is. If you do the same for all 3 of these unique answers, we get minus 1.24 plus 0.22i. So again, we're minus 1.24 away. Looks about okay. And we're up 0.2, only a small amount up. That's that point there. And if we put in 290, we would get 0.43 minus 1.18i. Again, does that one look okay? 4 and down 1.1. Yeah, not too bad. Probably a little to the left. That was the one. My drawing's a bit bad on that one. But all roughly okay. There are 3 different answers. Now, if the exam is nice to you, they'll let you leave the answers like this. Well, I'd like to write that out 3 times. If they're not, they want you to do a little extra work. They'll make you put the answer like this. But probably the exam, if they make you put the answer like this, they'll give you nicer numbers. If they make you put the answer like this, they'll give you numbers something like I've given you here. Okay, so that's how we get the cube root. That's how we get to the power of any number we want. This would have worked the same with 1 over 6. We would have just got 6 answers. 1 over 2. We already looked how to get the square root. This is a new way. Again, that other time we got 2 answers for a square root. We could do it this way, a lot easier in this way, I would say. Using the Moivre's theorem is so powerful. That's why it's so useful to write it this way. Okay, now that's a complicated class. That's the last class we're going to do on complex numbers. So if you have any question on this, on anything in this section, please put in the comments below. I'll do my best to get back to you. I'll hopefully answer anything you have. Until next time, have a good day.